Right now, you're moving at 1.3 million miles per hour through space. You can't feel it. You're not holding on to anything. But every cell in your body is hurtling through the cosmos at speeds that would make a bullet look motionless. And here's what nobody tells you. The Milky Way, our home, our fortress, our 100,000 light-year sanctuary, isn't racing through space because it wants to. It's running because something far more massive is hunting it. Tonight, we're going to flip the script on everything you think you know about our galaxy. Forget how big is the Milky Way. That's the wrong question. The real question is, why does the Milky Way need to be this big to survive? Because here's the truth hidden in the astronomy textbooks. Our galaxy didn't grow this massive by accident. Every star it consumed, every dwarf galaxy it cannibalized, every billion years of violent expansion, it was all preparation. The Milky Way has been building armor for a battle it's been fighting since before Earth existed. Most videos will tell you the Milky Way is one of the largest galaxies and leave it at that. But that's like saying a soldier is well equipped without asking why they're armed in the first place. So let's start with what you need to understand. The universe doesn't care about size. It cares about survival. And the Milky Way size, that's not a trophy. That's a life raft. Before we dive in, if you're ready to see the cosmos differently, hit that subscribe button and drop a comment below with your biggest question about space. Your engagement keeps these deep dives coming, and I read every single comment. Now, let me show you something that'll change how you see that band of light across the night sky forever. Let's talk about something most people miss. The Milky Way isn't sitting still. Our galaxy is currently traveling at approximately 600 kilometers per second relative to the cosmic microwave background. That's the leftover radiation from the Big Bang itself. To put that in perspective, we're moving roughly 370 times faster than the speed of sound. In 1 hour, the Milky Way crosses 2.16 million kilometers of space. But here's where it gets interesting. We're not just drifting, we're being pulled. The Milky Way, along with thousands of neighboring galaxies, is falling toward a gravitational anomaly so massive that scientists call it the Great Attractor. This isn't science fiction. This is measurable, observable reality happening right now. Every second, we fall 600 more kilometers toward this cosmic drain. Now, most videos would tell you about the Milky Way's size, first 100,000 light years across 400 billion stars, barred spiral structure. That's all true. But knowing those numbers without understanding why they matter is like memorizing your car's horsepower without knowing you're in a race. The Milky Way's mass, estimated at 1.5 trillion times the mass of our sun when you include dark matter, isn't random. Smaller galaxies get ripped apart by these gravitational currents. Medium-sized galaxies get stretched into tidal streams and absorbed. Only galaxies with enough binding energy, enough gravitational self-control, can hold themselves together while falling at these speeds. Think of it like this. Imagine you're whitewater rafting down a cosmic river. The small rafts, those are dwarf galaxies with only a few billion stars, they flip and break apart. Medium rafts barely hold together. But a massive, reinforced vessel, that stays intact. The Milky Way is that vessel. And it didn't become massive by luck. Over the past 13.6 billion years, our galaxy has consumed between 5 and 11 major dwarf galaxies and countless smaller stellar systems. Right now, astronomers can identify the remains of the Sagittarius dwarf galaxy streaming through our galactic disk. The Gaia-Enceladus merger 10 billion years ago added an entire galaxy's worth of stars to our halo. This wasn't conquest. This was fortification. Every consumed galaxy added mass, added binding energy, made the Milky Way harder to tear apart as it races towards structures millions of times more massive than itself. Most galaxies in the universe, 95% of them, in fact, are smaller than the Milky Way. They're dwarf ellipticals, or irregular galaxies containing just a few billion stars. The Milky Way sits in the top 5% by mass. That's not by chance. Size isn't about dominance, it's about endurance. Drop a comment. Did you know the Milky Way is moving this fast right now? What other cosmic facts blow your mind? Here's a question nobody asks. Why aren't there more giant galaxies? If bigger is better for survival, why isn't the universe filled with massive galactic titans? Why are 95% of galaxies tiny dwarfs, barely holding together? The answer reveals something crucial about our home. Galaxy formation follows a brutal logic. Only certain conditions allow a galaxy to grow large. You need to form early in the universe's history when gas was abundant. You need to be in a region with enough matter density to gather mass. And critically, you need to avoid the most violent regions where collisions would shred you before you could grow strong. The Milky Way threaded this needle perfectly. We formed about 13.6 billion years ago in what's now called the local group, a relatively quiet gravitational neighborhood containing about 80 galaxies. Compare that to the Virgo cluster, which contains over 1,300 galaxies packed into a region only 15 million light-years across. In Virgo, galaxies collide constantly. Ram pressure stripping tears the gas out of smaller galaxies, leaving them unable to form new stars. They become red and dead collections of aging suns with no future. The Milky Way avoided that fate by being in the suburbs. The local group gave us enough nearby mass to grow through mergers, but not so much violence that we'd be destroyed in the process. But here's the paradox. Being in a quiet neighborhood doesn't mean you're safe from the bad parts of town. The local group itself, all 80 galaxies and 10 million light-years of space, is falling as a single unit toward the Virgo supercluster at 300 kilometers per second. And Virgo? It's falling toward the Shapley supercluster, a gravitational monster containing 8,000 galaxies and sitting 650 million light-years away. Think of cosmic structure like this. Galaxies cluster into groups. Groups cluster into superclusters. Superclusters flow along filaments toward even larger concentrations of mass. It's gravity all the way down, and everything is falling toward everything else. The Milky Way's mass, that 1.5 trillion solar masses, determines whether we survive these falls intact or get shredded into stellar streams. Computer simulations show that galaxies below a certain mass threshold get torn apart by tidal forces as they fall through these larger structures. Above that threshold, they survive, but only if they're massive enough. The Milky Way sits just above that survival line. We're large enough to hold together, but not so large that we became a target for even bigger predators early in our history. This is the survival threshold. Below it, you dissolve. Above it, you endure. And the Milky Way has been dancing on that edge for billions of years, consuming just enough mass to stay safe without attracting the kind of attention that gets galaxies destroyed. If you're learning something new, smash that like button and share this video with someone who loves space. Let's spread cosmic knowledge. Let's zoom out for a moment and see where the Milky Way actually sits in the cosmic structure. Because understanding our neighborhood is key to understanding why we needed to grow this large. The local group is falling toward Virgo. Virgo is part of something called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster containing roughly 100,000 galaxies spanning 520 million light-years. And every single galaxy in Laniakea is flowing like water toward a central gravitational basin. Imagine the universe as a vast network of rivers. Galaxies are like boats carried by gravitational currents. Some currents are gentle, others are violent rapids. The Milky Way happens to be in a relatively calm current right now, but we're heading toward rougher waters. Laniakea isn't the end of the structure either. It's part of even larger flows toward the Shapley supercluster and other massive concentrations. When you map the universe at the largest scales, you see what astronomers call the cosmic web filaments of galaxies stretching across hundreds of millions of light years, surrounding enormous voids where almost no galaxies exist. The Milky Way lives on one of these filaments. We're connected through gravity to thousands of other galaxies, all of us flowing together through space-time toward the densest regions of the cosmic web. Now here's what makes the Milky Way special in this context. Most galaxies on these filaments are small. They're the cosmic equivalent of debris being swept along by a current. The Milky Way, by contrast, is more like a ship with its own propulsion, massive enough that while we're still being carried by the current, we're not completely at its mercy. This matters for our future. In about 4.5 billion years, the Milky Way will collide with Andromeda, our nearest large galactic neighbor. This collision is inevitable. Both galaxies are gravitationally bound to each other, and we're approaching at 110 kilometers per second. When we merge, the combined system, sometimes called Milkomeda, will contain about 1 trillion stars and be significantly more massive than either galaxy alone. This isn't destruction, it's evolution. The merger will make us more resistant to tidal disruption as we continue falling through larger structures. Think of it as two medieval castles combining their forces before a siege. Separately, each is strong. Together, they're formidable. This is the architecture of motion. Galaxies don't just sit in space. They flow, merge, grow, and adapt. The Milky Way's current size is a snapshot of this ongoing process. We're not done evolving. In 5 billion years, we'll be part of something larger and more resilient. And that's exactly what survival in this universe requires. Constant adaptation to forces beyond your control. Comment below. What do you think a galaxy merger would look like from Earth's surface? Would we even notice? Now, let's address the elephant in the room. Is the Milky Way actually large, or does it just seem large compared to its tiny neighbors? Both are true. And understanding this paradox is crucial. The Milky Way contains roughly 400 billion stars and spans 100,000 light years. By any reasonable standard, that's enormous. Light itself, traveling at 186,000 miles per second, takes 100,000 years just to cross from one edge to the other. Now compare that to a typical dwarf galaxy. The small Magellanic Cloud, one of our satellite galaxies, contains only 3 billion stars and measures about 7,000 light years across. That's roughly 130 times fewer stars and 14 times smaller in diameter than the Milky Way. Dwarf galaxies like this aren't rare. They're the default. The universe is absolutely packed with small galaxies. For every large spiral, like the Milky Way, there are probably hundreds or thousands of dwarfs. So yes, compared to the typical galaxy, the Milky Way is genuinely massive. We're in the top 5% by mass. That's statistically exceptional. But now let's compare ourselves to the real giants. IC 1101. One of the largest known galaxies, spans about 6 million light years and contains an estimated 100 trillion stars. That's 60 times wider than the Milky Way and 250 times more stars. If you placed IC 1101 where the Milky Way is, it would engulf Andromeda and extend far beyond any of our neighboring galaxies. M87, sitting at the center of the Virgo cluster, contains about 1 trillion stars. Its supermassive black hole weighs 6.5 billion solar masses. That's more than 1,600 times heavier than Sagittarius A asterisk. The black hole at our galaxy's center, these giant elliptical galaxies form through countless mergers over billions of years. They're the apex predators of the galactic ecosystem, sitting at the centers of massive clusters and consuming everything that wanders too close. Compared to these titans, the Milky Way is medium-sized. Not small, but definitely not the biggest kid on the block. Here's where the paradox resolves. The Milky Way is large enough to matter, but not so large that it became a target. We're massive enough to survive gravitational currents and tidal forces, but not so massive that we attracted attention from even bigger predators early in our evolution. This is the Goldilocks zone of galactic mass. Too small, and you get ripped apart. Too large, and you end up in violent regions where constant collisions transform you into something else entirely, usually a giant elliptical at the center of a cluster. The Milky Way is just right, large enough to protect the fragile chemistry of life, stable enough to allow billions of years of peaceful stellar evolution, and positioned perfectly to give rise to consciousness. Hit that like button if you're realizing the Milky Way size is perfect for life. Share this with a friend who needs their mind blown. Here's something most people miss when they talk about galaxy size. What you see isn't what you get. The Milky Way's visible matter, stars, gas, dust, makes up only about 10–15% of its total mass. The rest? Dark matter. We can't see dark matter directly. It doesn't emit light or interact with electromagnetic radiation. But we know it's there because galaxies behave in ways that only make sense if they contain far more mass than we can observe. Stars in the outer regions of the Milky Way orbit faster than they should based on the visible matter alone. By all rights, they should fly off into intergalactic space. The fact that they don't means something invisible is holding them in place through gravity. That something is dark matter, and it forms a massive halo, extending perhaps 300,000 light years from the galactic center, 3 times wider than the visible galaxy. Think of the Milky Way like an iceberg. The visible part, the stars and gas clouds, is the tip above water. The dark matter halo is the massive structure beneath the surface, providing the gravitational foundation that holds everything together. This dark matter halo is what actually determines the Milky Way's ability to survive in the universe. When we say the Milky Way has enough mass to resist tidal disruption, we're really talking about the dark matter. The stars are just passengers. Computer simulations of galaxy formation show that dark matter collapsed first, creating gravitational wells where normal matter could fall and form stars. The cosmic web itself, those filaments connecting superclusters, is primarily a dark matter structure. Galaxies trace the dark matter distribution like lights on a Christmas tree. The Milky Way's dark matter halo likely contains about 1 trillion solar masses. Combined with visible matter, that brings our total mass to roughly 1.5 trillion solar masses. This is the number that determines our fate as we fall through larger structures. Interestingly, dark matter halos don't grow indefinitely. They reach a maximum size determined by the local density of the universe. The Milky Way's halo is probably near its maximum growth, unless we merge with another large galaxy like Andromeda. What's fascinating is that we exist in a galaxy where the dark matter halo is large enough to provide stability, but not so large that violent interactions early in the universe's history would have disrupted star formation. Once again, the Milky Way sits in that Goldilocks zone. The dark matter scaffolding is the hidden architecture that makes everything else possible. Without it, galaxies couldn't exist. Stars couldn't form. Planets wouldn't orbit in stable systems. Life wouldn't arise. When you look at the Milky Way, you're seeing the tip of a massive cosmic iceberg. And that invisible foundation is what keeps us safe. Drop a comment. What do you think dark matter actually is? Scientists still don't know for sure. Let's talk about something uncomfortable. The Milky Way might be one of the largest galaxies in the universe, but it's also one of the most isolated. The nearest large galaxy, Andromeda, is 2.5 million light years away. In cosmic terms, that's relatively close. We're gravitationally bound and will eventually merge. But in practical terms, it might as well be infinite. Light from Andromeda takes 2.5 million years to reach us. That means when you look at Andromeda in the night sky, you're seeing what it looked like when early humans were just beginning to use stone tools on Earth. You're looking into deep time. If a civilization in Andromeda pointed a radio telescope at us and listened, they wouldn't hear any of our modern broadcasts. They'd be receiving radio waves that left Earth 2.5 million years ago, long before humans existed. Our television and radio signals have only been traveling for about 100 years, meaning they've reached stars within a 100 light-year radius, a tiny bubble in a galaxy 100,000 light-years across. This is the isolation effect. Even though the Milky Way contains hundreds of billions of stars, the distances are so vast that meaningful communication across even our own galaxy would take tens of thousands of years. Now consider the nearest galaxy beyond the local group. That's the Maffei 1 galaxy, about 10 million light years away. Any signal traveling between our galaxies would take 10 million years each way. By the time a reply arrived, the civilization that sent the original message would likely be extinct. The universe is 93 billion light years across, at least the observable part. Most galaxies are billions of light years away. Even traveling at light speed, which is physically impossible for anything with mass, you could never reach most galaxies. The expansion of space would carry them away faster than you could travel toward them. This means the Milky Way, despite being part of structures containing thousands or millions of other galaxies, is fundamentally alone. We can observe those other galaxies, we can study them, but we can never visit them. Our galaxy is an island universe, connected to others only by the invisible threads of gravity. This isolation might actually be good for life. In densely packed environments like the Virgo cluster, where galaxies constantly interact, conditions are chaotic. Gas gets stripped away, stars are disrupted by close encounters. The radiation environment is harsher. The Milky Way's relative isolation, part of a small group rather than a massive cluster, has given us billions of years of relative stability. The Sun has orbited the galactic center about 20 times since the solar system formed, and during all that time, we've avoided major disruptions. Sometimes being alone in a quiet neighborhood is exactly what you need to survive. Share this video if the scale of cosmic isolation gives you the chills. And subscribe for more mind-bending space content. Here's a question that'll mess with your head. How long would it take to cross the Milky Way? The answer depends on your speed, obviously. But let's run through some scenarios to understand just how vast this galaxy really is. Traveling at highway speed, say 70 miles per hour, it would take you about 1 trillion years to cross the Milky Way. That's roughly 70 times longer than the current age of the universe. Traveling at the speed of the fastest spacecraft humans have ever built, NASA's Parker Solar Probe, which reached 430,000 miles per hour, would take about 163 million years. That's about as long as the entire reign of the dinosaurs. Traveling at 1% the speed of light, which is incredibly fast and would require technology we don't yet possess, would take 10 million years. Modern humans have only existed for about 300,000 years. So this is still 33 times longer than all of human history. Even at the speed of light itself, 186,000 miles per second, the absolute cosmic speed limit, it takes 100,000 years to cross from one edge of the Milky Way to the other. This is the time problem. The galaxy is so large that meaningful exploration, even with theoretical technology, would take longer than human civilizations typically last. The entire recorded history of human civilization, from the first cities in Mesopotamia to today, spans about 10,000 years. That's 0.01% of the time it would take light to cross the galaxy. Now multiply this by the number of stars, 400 billion. Even if you could visit one star per second, working 24/7 without stopping, it would take 12,680 years just to visit them all. And you'd still be moving at impossible speeds to accomplish that. The Milky Way isn't just large in space, it's large in time. The distances translate into temporal barriers that make the galaxy effectively unexplorable in any single civilization's lifetime. This is why, despite containing hundreds of billions of stars and potentially trillions of planets, the Milky Way might be filled with civilizations that never meet each other. The universe has given us a galaxy with enough stars to make life probable, but spread them out so far that intelligent species remain isolated. It's both hopeful and heartbreaking. We're probably not alone, but we might never know. The Milky Way's size becomes less about pride and more about perspective when you measure it in time instead of distance. We're living in a structure so vast that the human lifespan is essentially zero compared to the time required to explore it. And yet, here we are, conscious beings who can measure these distances, calculate these travel times, and wonder about what else might be out there, forever beyond our reach. Comment below. If you could visit any star system in the Milky Way, which constellation would you choose? Let's dream together. Let's talk about something that changes everything we've discussed. The universe is expanding, and that expansion is accelerating. This isn't theoretical. We've measured it. Distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This is happening because space itself is expanding, carrying galaxies along with it, like dots on an inflating balloon. Right now, galaxies beyond about 15 billion light years are receding faster than the speed of light. That doesn't violate relativity because they're not moving through space that fast. Space itself is expanding between us and them. This creates what astronomers call the cosmic horizon. Galaxies beyond this horizon are moving away so fast that their light will never reach us. They're being carried beyond the observable universe, disappearing from view forever. Here's what that means for the Milky Way. The universe we can see is shrinking. Every year, about 20,000 galaxies cross the cosmic horizon and disappear from the observable universe. They still exist, but we can never see them, visit them, or communicate with them. They might as well not exist from our perspective. In about 100 billion years, every galaxy outside the local group will have been carried beyond the horizon. Future astronomers living in Milkomeda, the merged Milky Way Andromeda system, will look at the sky and see nothing but their own galaxy, surrounded by empty darkness. They'll have no way to know that the universe is larger than what they can see. They'll have no evidence of the Big Bang, no cosmic microwave background, no distant galaxies showing redshift. They'll be back where humanity was 500 years ago, thinking their galaxy is the entire universe. The Milky Way's size, impressive as it is, will eventually become the entire observable universe for whatever civilizations exist in that distant future. The context we have today, knowing we're part of something larger, will be lost. This is the expansion boundary, a horizon beyond which nothing can be known, and it's closing in. But here's the silver lining. Right now, in this brief cosmic moment, we can see the full structure of the universe. We can observe galaxies billions of light years away. We can measure the cosmic web. We can understand our place in something vast and wonderful. We're living in the golden age of cosmic observation. In the deep future, that won't be possible. So when we talk about the Milky Way being large, we need to remember, large relative to what? Someday, it will be the only reference point. The entire observable universe will consist of just our local galactic neighborhood. Right now, we have the privilege of seeing beyond that boundary. That makes this moment in cosmic history incredibly special. If this blew your mind, hit subscribe and turn on notifications. Every video explores another cosmic mystery. We've spent this entire journey talking about how large and impressive the Milky Way is. But let me leave you with a different perspective. It's also incredibly fragile. Despite containing 400 billion stars and enough mass to resist tidal disruption, the Milky Way exists in a delicate balance. Remove one key element, the dark matter halo, the current velocity through space, the isolation from violent cluster environments, and everything falls apart. Our sun orbits in what astronomers call the galactic habitable zone, a region far enough from the core to avoid deadly radiation and stellar collisions, but not so far out that heavy elements are scarce. We're in the Goldilocks zone of our own galaxy. Earth itself is even more improbable. Liquid water, stable climate for billions of years, a protective magnetic field, a large moon stabilizing our axial tilt, Jupiter acting as a cosmic vacuum cleaner, sweeping up asteroids that might otherwise hit us, layer upon layer of cosmic luck. And this fragile oasis exists inside a galaxy that's racing through space at 1.3 million miles per hour, falling toward gravitational attractors millions of times more massive than itself, all while navigating a universe that's actively trying to tear structure apart through expansion. The Milky Way is a fortress, yes, but it's a fortress under siege. In 4.5 billion years, we collide with Andromeda. The solar system might be flung into intergalactic space or consumed in the merger's chaos. Either way, Earth's comfortable orbit becomes unstable. In 15 billion years, we merge with the Virgo cluster, and the gravitational chaos makes our current environment seem peaceful by comparison. Eventually, dark energy will overcome even the strongest gravitational binding, tearing apart everything from superclusters down to individual galaxies. But here's what matters. Right now, in this moment, the Milky Way is protecting us. Its mass keeps us bound together. Its isolation gives us stability. Its size creates enough stellar diversity that elements like carbon, oxygen, and iron exist in abundance, elements necessary for life. The Milky Way size isn't just impressive, it's necessary. A smaller galaxy wouldn't have enough binding energy to survive what we're falling toward. A larger galaxy would likely be in a more violent environment. Once again, we're in the Goldilocks zone. Just the right size, just the right place, just the right time. When you look at the Milky Way tonight, that band of light stretching across the darkness, you're not just seeing a large galaxy. You're seeing a carefully balanced system that has protected Earth for 4.5 billion years while hurtling through a violent universe at impossible speeds. You're seeing home. And home is exactly the right size. Before you go, drop a comment sharing your biggest takeaway from this video. Subscribe for weekly cosmic deep dives. Share this with someone who needs to see the universe differently. And remember, we're all traveling through space together on this fragile fortress we call the Milky Way. Until next time, keep looking up.